Hello guys, welcome back to my channel. In this video, I'm gonna sort of break apart from the Laplace transform streak and I'm gonna redo the talk that I gave at the math club here at Cornell. So the first bit of the talk had a recap of single valued complex functions, but we have those series of videos on my channel. So I'm just directly gonna skip over all of that. If you don't know certain terms, basic ideas for single valued functions, then please watch those videos again and then come back to this one because I want you to at least get the most of it. If you feel like you don't understand some part of it, that's fine. This is lots of stuff condensed into one talk. So again, let's get started. Okay, so consider the complex function f of z equals say z squared. This is one function, and consider another g of z to the 1/2. Now if we write z in its polar form, so I have a magnitude and a phase, which I will denote like this. So notice what happens to f of z. That's just magnitude of z squared, and notice what happens to the phase. You have to multiply, if you substitute this in, by a factor of 2. And g of z is the square root of z e to the I phi divided by 2. So I have to divide this phase by 2. Now, one question you may have if you have a really good eye is, what branch do we take for the square root? What branch or what value? Is it the plus? Is it the minus? Well, the magnitude is always positive, so it's like the radius. So we just take the positive. But this question of the branch is really important. It's the essence of what multivalued functions are. Okay, so good question, good eye if you had that. So now what I want to do is I want to take tours on this contour. Say contour where the magnitude is a constant. So this is a circle, a family of circles. Centered at z equals 0. Okay, so we're just going around here. This is z equals 0. We're going around in an anti-clockwise direction because that's positive this way. So here, say this is the real axis. At this point, our phase is 0, phi is 0. So when phi is 0, f of z is just magnitude of z squared. G of z is just square root of magnitude of z. Okay, and then we take an entire rotation. So we do an entire rotation. We come back to where we started, but it's not exactly where we started. The phase has changed by 2 pi to denote one complete rotation. So f of z is magnitude z squared e to the 4 pi I. E to the 4 pi I is 1 again. So there's magnitude of z squared. Something interesting, we would expect the same value for g of z, but it's not really the case because you have this and then you have pi I because you divide the phase by 2, which is negative. So we have a negative value, and this is distinct from what we had for when we started at 0, at phase 0. That's really interesting, isn't it? What if we do another rotation? 4 pi. I'm just having different colors to make it look nice. Do another rotation. So f of z, magnitude z squared e to the, let's see, I believe 8 pi I is still magnitude z squared. G of z is going to be 2 pi I, which is 1, so just square root of z. So we've gotten rid of the minus sign. So there's something really funny going on here. G of z changed the sign so that after one rotation, f of z does not change. G of z, for G of z, we have to consider the negative branch. And then another rotation where f of z is unchanged throughout all these rotations. G of z, we have to consider the positive branch again. And this is the branch we started with at phi equals 0. So what that says is you need 2 rotations to get back to the initial value, where for f of z you need 1. So let me just write that down. So 1 rotation, and then f of z is sort of, you come back to whatever you had, but you need 2 rotations for g of z to come back. If you do 1 rotation, you end up with some different branch. Okay, so this was just one function. Let's sort of do another function, and then we can probably generalize. So let's say g of z is z minus 1 to the 1/3. Before we toured on, we sort of went around on this contours that obeyed this condition. Here we're going to obey this condition. So the point around which you're doing rotations is also important. So the point of rotation is important. We're going to tie these terms together when I come to the formalism is a constant. What this gives me is a family of circles centered at z equals 1. So that's going to be somewhere here. This is my origin. It's going to be here. Z equals 1. Anti-clockwise direction. So say at here phi equals 0. Phi equals 0, we have g of z. I'm writing it in the polar form directly. So when I parameterize it, it's gonna look like this. It's gonna or let me just parameterize in a different way maybe. So if we are going around in a circle centered at z equals 1, we have to parameterize this as some radius. So I'm going to call that maybe mod r e to the I phi. Yes. So when I do that, I have cube root of mod r e to the I phi over 3. I have to divide by 3 now because we have a cube root. So when phi is 0, this guy is just cube root of mod r, because this is e to the I phi. E to the I 0 is 1. Now when phi is 2 pi, you have this, but then e to the I 2 pi over 3, which is not really 1. Fine. What about 4 pi? Well, you expect we should return to the same, right? If we compare it to the example we did before. Well, not really. This is not 1 again. Well, no matter. Stuff happens all the time. And we're mathematicians, we have to account for the stuff like this. So another rotation. So that's what, one rotation, two rotations, and third. This is the third rotation complete. And we end up with e to the I 6 pi over 3, which is 2 pi for the phase, which is essentially the start point. So you notice this cube root, or whatever we divide the phase by, has to do with the number of rotations we have. So assuming you have some function, maybe like some polynomial here, some polynomial raised to 1 over n, where n is greater than 1, then we have to do n rotations, so n times rotations around specific points. And if you have a clever eye, notice the points we pick. We picked the point z equals 0, such that the inside guy was a root. So it has a root at z equals 0. We have a root here at z equals 1. So specific points are the roots of p of z. And notice the number of rotations we take are also the number of distinct values. In the case of the square root, there were two distinct values, the positive branch and the negative branch. For the cube root, it's a little more complicated. We can't really call it a negative branch. There's a 2 pi over 3 branch, this 120 degree branch, and a 240 degree branch, and then finally a 360 branch, which is essentially sort of the one we started with. So there's one distinct, so this is equal to the 0 branch, and then two of these, the 120 and the 240 branch. So again, now it's time to really define things properly. So functions g of z in both the cases are examples of multivalued functions. F of z in the first example, the z squared, is a single valued function. So a multivalued function is a function that changes its value per rotation around a specific point. I'm going to define the specific point when I come to the formalism, but it's not the same point for different functions. And f of z are basic. You can say they are special cases of multivalued functions where there's just one distinct value. So the square root, we had two distinct values. That's a two-valued function. Cube root is a three-valued function with three distinct values. Single-valued functions are multi-valued functions of just one value. So that's just single-valued functions. Again, one point I want to make is classically, see, these functions are not really functions because they don't really pass the vertical line test. Take the example of the square root function, for example. At one given time, we just consider one branch, and then we consider the other branch separately, so that we just have either this part or that part from this. But here we're sort of, the idea is the same. We consider just one piece of the range at a given time. So when we're doing a rotation, say we're doing the first rotation where phi equals 0, we consider the positive branch because that's the way, sort of the magnitude or whatever works. Then we do the second rotation, then we actually considering the negative branch. And then for the final rotation, we're back to the positive branch. The end of the first rotation, we sort of start with the negative sign, and then the entire second rotation we have that negative sign, so we're working on that negative range, and then when we reach back, we again back to the first range that we started with. So this idea of changing ranges per rotation is really important. It will help us with our formalization. So that's the idea. They're still, don't really pass the vertical line test. You consider them together, but we sort of consider just one piece of the range at a given time, per rotation around that specific point. So let's move on to the formalism now. Okay, so here's the formalism. So for this function, for example, the point we chose to go around was this. For this, it was this. These points are called branch points, because it's passing through them that we change the branch. And I'm going to define a few things. Definition: branch points are the points such that a multivalued function changes its branch, and branch is the same as the branches of the square root, or the distinct values, after making one complete rotation. So that's the definition. There's one claim I'm gonna make. Branch points always come in pairs, but if there is a single branch point, it is always paired with infinity. Well, now a good question is, what infinity? Plus infinity, minus infinity, or the imaginary infinities, plus and minus? Well, the thing is, it's actually doesn't matter. Why does it not matter? Because we're not looking at the complex plane as some plane that's isomorphic to R2. Of course, it is isomorphic to R2, but we're not really looking at it in this way. We're instead looking at it in terms of a stereographic projection. So what's a stereographic projection? So consider a sphere and a plane. So we have to map the plane onto the sphere. So what we do is we take this line, we take the North Pole, we draw a line from the North Pole to any given point on this plane. And the point where this line intersects the sphere, any point on the surface of the sphere, that's the mapping of this point here on the plane to the sphere. So in this case, you see this point. Maybe let me take another color. We all see this point, right? And we connect a line from this point to the North Pole, and it intersects somewhere here. So that's the mapping of this point onto here. So we do that for all the points on the plane, and you get the entire sphere. Why is this important? Because look at infinity. Infinity is somewhere like really far. You have a line that's connecting infinity to the North Pole. It's always going to be parallel, so it's not going to intersect the sphere at any point. So you can think of infinity being mapped to the North Pole, and that holds for any infinity. This is positive infinity. Same thing for negative infinity, and same thing for the imaginary infinities as well. So all the infinities are sort of mapped to this, crunched down to this one North Pole here. And this sphere, by the way, that the complex plane gets mapped to is the Riemann sphere. It's a complex manifold for higher dimensions. So manifolds are higher dimensional generalizations of surfaces. So it's a complex manifold if you want to work with not two variables, like not just one z, but many variables, several variables for complex functions. But that theory is way more complicated. We won't talk much about that. So this is the Riemann sphere. If we consider this stereographic projection from the complex plane to the Riemann sphere, then these infinities don't really matter because all of them are mapped to the North Pole. So we just pair one point to the other. And now let me just talk about some other aspects of this generalization. So definition. Curves connecting pairs of branch points are called branch cuts. So the idea is that the function, the multivalued function, changes its branch if it crosses a branch cut while rotating about the specific point, the specific point of rotation was the branch point. So now let me give you an example. The branch cut for the square root function is at 0. So the one branch point at 0, the other is at infinity. Branch cut is sort of to connect the pairs. So branch cut can be a straight line, that's the simplest case. But it doesn't have to be. We can deform it because since it's complex analysis we're working with, it's generally going to be analytic everywhere in between. So we can deform it in any weird way we want. This is still going to be a valid branch cut. But the idea is any contour we drew that was centered at 0, those were the contours we went around. They always pass through this branch cut here. And whenever they pass through the branch cut, which happened at here, at say the phase 0 point, that's where we had to change the value, right? That's where we had to account for the different phase. And then because of the different phase, we would have a negative or a positive sign. So we would change the branch whenever we went around. For the cube root case, z minus 1 cube root, the branch because it is at 1 and infinity. Maybe let's take negative infinity because it doesn't matter here. And if I take a contour that's centered at z equals 1, any direction I go, we're always going to run into that. And the size doesn't matter. See, that's the role of the infinity. The size doesn't matter. Even if this were arbitrarily large, the radius of this circle centered at 1, it wouldn't matter because the branch cut's extending to infinity. So you either run into 1 here if you put your branch cut here, or you run into the branch cut here. If you place your branch cut from 1 to positive infinity, you're always going to run into that while you're rotating. And because of you running into that, after one complete rotation, it's going to change the value. It's going to change the branch after intersecting with this. So that's the That's the formalism. That's the way we look at this stuff. Now, a Riemann surface is a good way of picturizing what happens to the range, because the range is the important thing here. So a Riemann surface is another complex manifold. I'm using the most general terminology that represents one branch of a multivalued function. So the number of Riemann surfaces for a given function is equal to the number of branches for a given function, or the number of distinct values it can take. So now, one way of looking at this, or a really nice way I like to use, is let's take the case of the square root function. So this is the range of the square root function, and this is, say, the domain. So this is the z plane. This is the positive, and as I said, there's two of those for two distinct branches. Let's do one for the negative. So what we do is, when we're rotating, so this is the branch point, we're rotating here, but what we need to account for is the branch cut in both the cases. Maybe have a branch cut here as well. So when we're going around, we complete a rotation, which means we start here, we end here. And we're sort of, when we want to connect this path, we encounter a branch cut. And when we encounter a branch cut, that's where we literally jump the sheet and we go to the negative branch. And then we start rotating again. So the z-plane doesn't really change. We're still on the z-plane because, we're still on the same circle in the z-plane. But for the range, whatever the square root maps to, it's not the same. We have a negative sign to whatever it maps to. So for the second time that you're rotating, you're going to be rotating here. You're going to be rotating like this. And when you encounter this branch cut here, again, that's where you jump back. Since there's no third Riemann surface, you're going to jump back to the one you had before. But you have to jump. You have to jump somewhere. So you're going to jump back here. And that's basically this rotation. Entire rotation is going to happen here. And we keep doing this. We encounter this here. We jump down. So here we were at the bottom. When we jump down, we're going to be at the top. So that's some sort of twisted continuity idea going on here. But probably a better example, and we can do this for the cube root as well. We have three Riemann sheets. Maybe have them like this, and maybe when we go around, z equals 1. Denote the Riemann, the branch cut in all of those, because it's important. It tells you when to jump. So one rotation, no problem. You encounter the branch cut, jump to the lower. You encounter one, but now there's a special place to jump as well. You can jump on the third. And after you encounter one on the third, you jump back to the first. You jump back here. And again, all of these are the distinct values for this cube root function. And this is the 120 branch. This is the 240 branch. A better idea, or a more visual representation of what's going on, is down here. This is the positive branch of the square root function. This is the negative branch of the square root function. So the branch cut is like here, is here. This entire gap that's left out. Here the branch cuts like the place between, here maybe. So what's happening when we go around the z-plane once? We start maybe here. And now here, in this case, we're considering the negative infinity branch cut. So we start here, there's no problem. We come here, there is an issue. We come here, there's an issue. So we have to jump to the lower sheet. The lower sheet is here. And you see this upper guy and this lower guy are sort of connected. If they weren't different functions, if they were the same function in an ideal universe, we could really stitch them together and connect them. And we come down here, there's no problem, We go all the way back again here. There where we run into this lower part also has the same branch cut going on. So this entire thing is like one branch cut. It's just hard to show here. And then when you run into that, that's where you jump back to this guy, the bottom portion. You see, from this we come to this. We're not jumping. There's no jump discontinuity in the square root. Wherever it's continuous, the branches are continuous. So we come here, no problems until we come here. And then we again come to the top guy here. So it's some sort of twisted Hot Wheels racetrack going on here. But the branch cut is literally the place where we would have stitched these two domains together, these two ranges together. And see that this is what happens when we stitch them together. And of course, we cannot really have something that's stitched up together because of the vertical line test, it wouldn't be really a function if we stitch them. But again, I want you to imagine the branch cut as the place of stitching. So the branch cut is where we stitch the two ranges for a multivalued function together. So this is the brilliant idea that this is the brilliant formalism that we're going to work with all the time. This was important, otherwise, how do we account for Cauchy-Riemann conditions and the Cauchy-Gursa theorem, or how does integral go to zero? If we do a contour around the branch point, we're not guaranteed to end up at the same point, so the integral may not even be zero. But then if you avoid the branch cut to resolve the paradox, then the integral is zero. Because if you cross it, you have to account for the extra phase change or the change in the value. So we don't really do that because it's tedious. We go around the branch cut. And that's the idea we're going to use later on. An interesting, a really nice example is the natural log function. So the natural log of z, in general, you may have noticed, h of z to the 1 over n has branch points at the roots of h of z, and there's n branches, so n sheets. Now the curious case of the natural log function is something like this. You polar decompose it, it's going to look like this. You have to add the phase because of the properties of the natural log. This is always positive. The branch point is at 0, so it's naturally paired up with infinity. So this, if we go around the z-plane again and again, after one rotation, we're going to have 2 pi I. After 2 rotations, we're going to have 4 pi I, and we keep doing that for n rotations. We're going to have 2n pi I, where n is some integer for the rotations, a positive integer, let's say. So we won't really, no matter how many rotations we do, we won't really get back to where we started off. So there's infinite Riemann surfaces because there's infinite branches for this. All of these are distinct values, right? These are not the same because they're different by the additive factor of 2 pi I. So there's infinite Riemann surfaces like this, and you won't really get back to where we start unless you reverse the rotation. But again, that doesn't count. We weren't reversing the rotation for the square root or the cube root. But this is a really nice example. We don't really rotate, we don't really return to the same value we started. We just keep going, keep going, keep jumping, keep jumping, keep jumping like that. It's a really nice example. Probably one of the only, the few examples where there's infinite Riemann surfaces in the range. Now, after we have this theory developed, I'm going to go to the heart of this talk, special functions. Many people really appreciate these things. So let me define something. Complex functions that have only simple poles as their singularities are called meromorphic functions. There's too many morphic things, there's holomorphic stuff. These are called meromorphic. So the number of poles can be, simple poles can be infinity, but they have to be simple. They have to be simple. Now, okay, because what this allows us to do is this really nice formula that we can derive. So assume f of z has simple poles. My handwriting. Simple poles at, say, zj, where j goes from 1 to n, and then capital N could be infinity, as I said. Then if we have some point z is not equal to any one of these for all j, the residue theorem gives us 1 over 2 pi I. This is not really connected to multivalued functions. So f c minus z dc is f of z, the pole at z from the denominator, plus the residues at all of these simple. So the residue of this at all of these for all the different j's. That's the residue theorem, where Cn is a contour containing the first n poles from this. And we assume that are arranged in increasing absolute value. So for simple poles, the residue calculation is pretty simple, right? We've done this a bunch of times. That's why I'm saying you should watch the videos for the single valued complex analysis. This is just multiply by the factor and take the limit, and factor to the power 1. No derivatives because it's order simple or simple pole, order 1. So what this gives you is zj minus z, because again this is not 0 because of this condition here, and limit as c goes to zj minus zj f of c. That's the residue. What we can do is we can literally substitute this on top. I'm just going to call this. I'm just going to call this, define this as rj over zj minus 0. Rj is like whatever this entire limit was. It's going to be finite. It has to be finite for this to be well defined. So when we plug this here, what we have to do, we have to subtract this from whatever we get when we plug z equals 0 in this expression. So when we do that, we have this that equals, we're going to have this minus f of c over c, because the z goes to 0 for the 0 case. So we find a common denominator there, simplify it significantly, f of c over c minus z c dc plus sum from j equals 1 to n. We should sum from this to n because we're enclosing n of those. Rj 1 over z minus zj plus 1 over zj. Fine. There's no, yeah, this is pretty much straightforward. It's subtracting. And now what I want to do is I want to take the magnitude of this guy to go to infinity. Or rather, what I want to do is I want to take the contour, radius of the contour Cn to go to infinity. When that happens, this guy approaches a finite value because it's analytic, it's bounded, it's integrable. Otherwise, none of this would really exist. This is finite. So this integral here, because of the denominator that's going to infinity, and the numerator that's bounded, it's growing slower than the denominator. Once we do that, Cn now encloses all the poles. And this guy goes to 0. So in the limit, this guy goes to 0. N now becomes capital N. So I'm taking f of 0 on that side, because now it encloses everything. And we have Rj 1 over z minus zj plus 1 over zj. This is a really important formula which is called the Mittag-Leffler expansion. You may remember I did a video on the Mittag-Leffler cotangent expansion in one of the Gamma videos I did before. This is a generalization, this is a general formula for that. Since a cotangent function, or I think a natural log of the sine satisfies something like this, or the other analog of this, the natural log analog of this, which I will talk about briefly. That's why we have a cotangent expansion, a Mittag-Leffler cotangent expansion. We need a function that's meromorphic, satisfied all these conditions like this. So maybe one simplification we can do, or one claim we can do, so let G be an entire function, which means it's non-zero everywhere, doesn't vanish anywhere. Or rather, not vanish everywhere. Entire means it's holomorphic everywhere. with simple zeros, then the claim goes that g prime of z over g of z is meromorphic. You can, and bounded for all values of z, because you can see this again. I haven't finished yet. For all values of z and its residues are all unity or 1. It's a really tall claim, but again, it's easy to see this if you consider g of z to be of the form z minus z1, z minus z2, z minus zn times h of z, where h of z is analytic and does not vanish anywhere for all z. And then you can sort of differentiate and see that we really can satisfy this claim. This really does satisfy the claim. So now, since this is meromorphic, we can use the Mittag-Leffler expansion just on the box term. So when I do that, I have the derivative of g of z, of natural log of g of z, which is precisely g prime of z over g of z, which is using the Mittag-Leffler expansion plus 1 to n. The residue is unity, so that really helps. R of j is 1, so we just forget that term. So g of z, you solve for everything, is g of 0 e to the cz product from j equals 1 to capital N, 1 minus z over zj e to the z over zj, where c is this thing, the derivative evaluated 0 divided by g of 0. So this is a really important formula, because this is what helps us to get the cotangent expansion for the Mittag-Leffler cotangent expansion, because we can write pi times cotangent of pi z, sum from n equals 1 to infinity, z over z squared minus n squared plus 1 over z. So it's using this and maybe some of the Mittag-Leffler, original Mittag-Leffler formula. So that's why this is like really important. Especially this, it's going to help us later when we go to gamma functions. Oops, spoiler alert. So now going on to the very first special function we have, the gamma function. It's defined as this integral. So it's called Euler's integral of the first kind, e to the z minus 1, e to the minus t dt. Well, the region of convergence is greater than 0. This is important when we want to do contours and all sorts of other things later on. Gamma is also called the factorial function because of this recursive relationship that it satisfies. So let's just build on the recursive relationship. Z plus 1, z plus 2, and so on. Z plus n minus 1, gamma of z, which we can just make gamma of z the subject of the equation with gamma of z plus n, z plus 1, z plus n minus 1. So you notice here, the numerator is analytic for a real part of z greater than negative n, and this is always going to be satisfied as long as we're in the first region of convergence. So we don't really need to worry about the numerator blowing up. What we need to worry about is the denominator. The form of the denominator implies that gamma of z has simple poles at z equals 0, z equals -1, -2 to minus n plus 1. So since there's just simple poles, the numerator does not really contribute to anything. Gamma of z is meromorphic. There we go. Since it's meromorphic, that's nice. We know this is entire with simple zeros at minus k, where k goes from 1 to infinity from the previous idea. And we can use the expansion we had before to come to this formula: 1 plus z over k e to the minus z over k, where 1 over gamma of z is z e to the small gamma of z, product from k equals 1 to infinity, 1 plus z over k e to the minus z over k. This is an important formula if you want to analyze the Franzen-Robinson constant, which is basically this. And this small gamma here is the Euler-Mascheroni constant. We don't know about the transcendentality of this. We probably know it's irrational, but if you can show it's transcendental, you can prove it, $1 million for you. Now, you can also note that this, which we defined, we know as the digamma function or polygamma of order 0, is meromorphic. So we can use the Mittag-Leffler again to have an expansion for this, or we can just take the natural log of this and then differentiate it. That's because then we get gamma prime of z over gamma of z. You can also do that any which way is possible. Now we have so many tools in our arsenal to do this kind of work. Before we had to sort of derive this and then take the natural log. Now we have a powerful expansion right from complex analysis, and we get an expansion for the digamma function. So there we have gamma digamma, just like my channel name. And it's easy to show from here that the digamma of 1 is negative Euler-Mascheroni, which is just this. So this is also digamma or polygamma of order 0. Now moving on to another curious function, the beta function. They're all related. This is called Euler's integral of the second kind, which takes two arguments, say a and b. We define this as integral from 0 to 1, t to the a minus 1, 1 minus t to the b minus 1 dt. Region of convergence is when real part of a is greater than 0 and the real part of b is greater than 0. It's easy to show the beta is symmetric in its arguments once you show that it's the product of gammas or a gamma of the sum of arguments. This is easy to show once you get the polar form. You write this in a polar form and you bunch them together. You take two gammas sort of multiply them together in polar form, and you basically get a beta times this gamma. And then showing the symmetry is simple. The product is symmetric, so just as the sum is. So this really helps us to give us this formula, because gamma of z and gamma of 1 minus z is beta of z 1 minus z is 2 times this integral, which I've cleverly used the substitution. I'm writing it in polar form. U to the 2z minus 1 over u squared plus 1 du. See, now we've run into our very first integral for a multivalued function, because z is not necessarily an integer. Z can be any real number that's in this range. So it's definitely not an integer. If you look at individual regions of convergence for the beta and both of the gammas, we want both of them to hold. We need to be here from 0 to 1. We need to be in this strip. We need to be in this strip. So it's definitely not an integer. Z is definitely not an integer. And this remember, this is going to play an important role when we evaluate this. That's right, we're going to actually evaluate this integral on a fresh page. See you there. So there we are with the integral. I'm going to define, forget the factor of 2 for now. We have this, where z is a complex number that's inside this region of convergence. So now let's define a complex function f of u as basically the integrand. So I've just drawn the contour here that we're going to take. So contour gamma f of u du is just this guy. But I've also marked with these hatched lines the branch point, the branch cut for the numerator, because that's the numerator is only going to generate a multivalued bit. So I'm going to connect it at positive infinity. We have a branch cut, but notice how we're going to go. We're going to go from 1 to this r here, and then loop back to the r at the bottom, and then go back. We're not going to cut, we're not going to intersect the branch cut, because we don't want to account for the different range. It's going to become tricky. So the trick with these integrals, avoid the branch cut at all costs. But we need to account for the change in phase here at the bottom segment. It's not the same as the top segment. They won't cancel out. That's just the specialty here. So this is just a residue theorem. 2 pi I is analytic everywhere, except at the pole we have at I, the poles we have at I and minus I. So residue f of u. So let's do segment by segment. For top segment, segment 1. This just can be parameterized as u2 to the z minus 1 over u squared plus 1 du, where u is real. So this is just I. Now for the loop part 2, the big closure, parameterize u as r e to the I theta as before. So this f of u du, integral from 0 to 2 pi, r I e to the I theta, r e to the I theta, 2z minus 1, r squared e to the 2I theta plus 1, d theta. You can use any argument you want. The integrand is bounded. The integral vanishes. The denominator will make everything go to 0 when we take the limit as r goes to infinity. For segment 3, this is the interesting case, because we're going from, let's see, infinity to 0. But since we're at the bottom guy, we need to account for the change in phase. So the multivalued numerator changes when it comes back to this point, and there's an infinitesimal gap between them. So it doesn't really, the gap really doesn't matter. It changes its phase by a 2 pi I factor. So we need to account for that. So u times 2 pi I to the 2z minus 1 over, if this were a square root, this would be a 1/2 factor, and then this would be e pi I, which would be minus, but this is not, this is a variable. We don't know what z is. We can separate the phase out and we get a minus e to the 2 pi I to the 2z minus 1 times I. So combining, but we're not done yet. There's part 4 that remains, the small epsilon circle. So u epsilon e to the I theta, that's the parameterization we use. So I write this out, all of this. So 3 pi over 2 to pi over 2, because of the orientation. Here's 3 pi over 2 and then pi over 2. Epsilon I e to the I theta. Epsilon e to the I theta. 2z minus 1 over epsilon squared to 2I theta plus 1 d theta. So as epsilon goes to 0, the denominator is 1, the numerator is 0. So this guy also goes to 0. So the parts we're concerned about that don't really die down, sometimes they have died down. And again, this region of convergence plays a role in keeping the bracketed factor in the numerator, because if it were in the denominator for part 2, it would have never really died down. So this is really important. So it's all connected to the choice of z that we had. Just like the Laplace transform, the region of convergence is like really nice. It works with everything that we had before. So finally, we connect everything together. We have 1 minus e to the 2 pi I to the 2z minus 1 times capital I is 2 pi I times, well, there's two residues, one's at I and the other's at minus I. So u minus I f of u plus limit u goes to minus I, u plus I f of u. And this you can simplify a lot, like really a lot. And I'm probably going to skip that step. You get pi over 2 times sine of pi z. But notice what we were working with initially, where this is 2 times I. So 2 times of this is pi over sine of pi z, and that's another way of proving the reflection formula for the gamma function. You can do a similar approach by just take the natural log and differentiate. You get the reflection formula for the digamma function. So consider this. This is going to be really important for us later on, because I'm going to talk about analytic continuation before we do anything else. Analytic continuation, I'm not going to use maybe I'll use a fresh page. So people think they know what analytic continuation is. It's like a nice term to throw around. But okay, let me give you some idea. So assuming f of z, a complex function, is analytic in some region S that is a subset of the complex plane, then there is a way to extend f beyond S. I mean, my analytic is that the Laurent series for f is equal to f. So the Laurent series converges to f in this region. Beyond it, we don't know. It may diverge. So here's the theorem. Some horrible handwriting right there. So let f of f1, f2 be complex functions from C to C, be analytic in a common region S if f1 equals f2 in a neighborhood of a point Z that belongs to S, or for a segment of a curve in S, then f1 equals f2 for all Z in S. But the corollary is way more interesting. The behavior of a function that's analytic in a region S is completely determined by its behavior in a small neighborhood of an arbitrary point in that region. Well, this says nothing. I need examples. So consider f1 of Z, sum from n equals 0 to infinity, Z to the n, the geometric series, which is, well, analytic, converges for absolute value of Z less than 1. It converges 1 over 1 minus Z. For this, it's undefined. It doesn't converge. Consider f2 of Z, sum from n equals 0 to infinity, 3 over 5 to the n plus 1, Z plus 2 over 3 to the n. Converges to 1 over 1 minus Z for Z plus 2 over 3 less than 5 over 3 and undefined elsewhere. So let me just draw the regions of convergence to give you an idea. So the first one is a unit circle centered at 1. It's a unit disk rather. The region of convergence is a disk. The boundary is a circle, but it's a disk for f1. For f2, it's also a unit circle, but it's centered at minus 2 by 3. So minus 2 by 3 is somewhere maybe here. So it's this green thing. And notice they have a region in common. All of region of f1 is included in the region f2. So they have that in common. So by the theorem we had before for analytic continuation, we can say that f1 and f2 are analytic continuations of each other. The way I see it is f1 is only restricted to this white disk. But since f1 and f2 share this common convergence value, in a region of convergence they share. Because of this, by the theorem above, we can extend f1 into f2. So now the analytic continuation region of convergence of f1 is this entire thing by analytic continuation, because they share a value in the common region. So f of z equals 1 over 1 minus z is the analytic continuation of both f1 and f2. So as long as they're in this big white region of convergence, that is the analytic continuation of f1, both of these will have this value. The series will have that value. It will converge to this. So this is a really nice example of analytic continuation. I hope you understand that. This is really important because we're going to apply it for the gamma function right now. So let's get on with it. So remember, we had this. Since we're in this region of convergence of real part of z that's stuck between 1 and 0, the common value that both z, gamma of z and gamma of 1 minus z will have is that gamma of z equals 1/2, because both of them will be gamma of 1/2, which is square root pi, the Gaussian integral. So the region of convergence of gamma of z is real part of z greater than 0. For gamma of 1 minus z is real part of z less than 1. And they have a common value at z equals 1/2. So analytic continuation, we can extend. This is all of the positive axis. This is all of the negative axis from 1. So since they have a common value of 1/2, or 1 here, so they have common values here in this region. They have common values here in this region. We can extend this gamma function onto the region of convergence of this gamma function, which is essentially going to be all of the negative plane, all of the negative axis. So we've extended gamma into the negative. There's justification for extending gamma into this region of convergence, and because of that we can find the negative values of the gamma function using this formula. So this we have minus pi over z times gamma of z sine of pi z. We can find gamma of, I believe, negative 1/2 gamma of negative 1/2 is minus pi over 2. Gamma of 1/2 is square root pi. Sine of pi over 2 is 1. So that just gives you minus 2 times square root pi. There we go. We've defined the factorial of a negative number. There we go. Isn't that fantastic? Isn't that nice? You can keep doing this for take an arbitrary value of z in this analytic continued region of convergence, and there you go, factorial of that. So this is why this is really important. Now the very last part of my talk was talking about the last special function, the Riemann Zeta function. So Riemann Zeta is defined by this infinite sum n to the z with the region of convergence where real part of z is greater than 1. So for x, for some real number variable x that's greater than 1, there's a formula like this. U to the x minus 1 over e to the u minus 1 du. We know the proof of this is simple. Use the geometric series for the denominator, and you'll get a gamma times the Riemann zeta on top. So the gammas cancel, you just get a Riemann zeta. Turns out you can also extend this to the complex plane. Because of the integral representation of the gamma function, which is valid for, which we just showed, the definition for the gamma function, which we showed was valid for a complex z. Because of this and the complex geometric series, which we used, which I just showed in the region of analytic continuation page. So because of that, we can have a formula for the gamma function that looks like this. Sorry, the Riemann zeta function that looks like this. So u to the z minus 1, e to the u minus 1 du, which I can sort of complexify, use the reflection formula a little bit and complexify, or have a contour integral setup, e to the minus u minus 1 du. You can see these are equal by integrating on the Hankel contour, where small gamma is the Hankel contour. Extremely useful contour. It's so useful they gave it a name. So it looks like this. And you're sort of avoiding the branch cut here. 0 to negative infinity branch cut generated by the numerator. And there's like several, there's I think infinite residues, infinite simple poles. That's why the gamma function is meromorphic as well, because you can see, judging by the integrand here, the denominator has a pole when it's equal to 1. So we have minus u equals to 2n pi I, where n is some integer. So it's infinite poles. This is the Hankel contour. So this is one representation of the gamma function. This is really useful because, say if we know, we already know that this is gamma of z times the Riemann zeta of z. So we integrate on the Hankel contour again. The top part is going from infinity to 0, and the variable will be real if we parameterize on the top segment dx, plus the bottom segment. I'm just like taking everything else to be 0. The outer closure, the small closure, all of that. I'm going to ignore the steps for now. They're easy to show. You can show them on your own. But the bottom segment will have this extra phase factor like before, z minus 1. And again, the region of convergence helps us to sort of set the outer and inner closures to 0. E to the x minus 1 dx. This gives us e to the 2I pi z minus 1 minus 1 times this. So that's gamma of z times Riemann zeta of z is equal to 2 pi I times the sum of residues of u to the z minus 1 or e to the u minus 1. And as I said, there's infinitely many of those. We just won't calculate the residue at 0 because we excluded that from the contour. So k is not equal to 0. We evaluate everything. We have 2 pi I k to the z minus 1. That's the sum here. It's a geometric series. We can simplify it So we have 2i pi z minus 1 minus 1 gamma zeta is 2i pi to the z 1 plus e to the I pi z minus 1 gamma, Riemann zeta of 1 minus z. And if you simplify a lot, using the duplication formula for the gamma function and stuff like that, you end up with this pi raised to 1 minus z over 2 gamma of 1 minus z over 2 Riemann zeta of 1 minus z pi raised to minus z over 2 gamma of z over 2 zeta of c, which you might remember from my Riemann zeta video series as the functional equation for the Riemann zeta. This is again really important for the reasons of analytic continuation. This is defined as a region of convergence greater than 1. This has a region of convergence less than 2. So greater than 1 is like here. Less than 2 is like here. Back. They share a common value of Riemann zeta of 1/2. So we can analytically continue Riemann zeta of z into the region of convergence for this Riemann zeta, which is the negative part of the plane. So we can continue analytically into real part of z is less than 0. And doing that, so that just justifies negative values of the Riemann zeta. We know some standard values of the Riemann zeta function. 1 over n squared is pi squared over 6. This is also proved by Fourier series, pi to the 4 over 90. Now this sum from n equals 1 to infinity, n is 1 plus 2 plus so on, sum of all positive integers, minus 112. You get that from this formula, literally this formula. Just plug everything in, just plug the right things in. And this is justified because of analytic continuation. Riemann zeta of minus 2, sum from n equals 1 to infinity, n squared, 1 squared plus 2 squared plus so on is 0. Zeta of minus 3 is n equals 1 to infinity n cubed, which is 1 cubed plus 2 cubed plus so on, 1 over 120. These values are really important when you're compactifying in string theory for those high dimensions that you're working in. This is 0 for all, for n, that's some positive integer. And these guys are called the trivial zeros of the zeta. There's also zeros where the real part of z is 1/2. On that strip, there's zeros, which is called the critical strip. So as I said, as I've talked about before, Riemann hypothesis was proving or disproving that all the zeros of the Riemann zeta are the trivial ones or the ones that lie on the critical strip. Now, showing the ones that lie on the critical strip, many people requested me. I actually tried it on my own. Turns out there's a special formula for the gamma function, a complex variable gamma function. There's one identity that only works out when the real part is 1/2. Sort of like the reflection, like how the reflection has a formula has both the gammas take the same value when z is 1/2. This number 1/2 is really important from then on, and then there's also a nice formula where z, real part of z equals 1/2, helps to cancel the crazy terms, and you end up with that. I might not make a video, it depends. It's part of my old notes when I used to be all fascinated by these things. But this again is the problem. Prove or disprove the Riemann hypothesis, and $1 million are yours. So maybe this video inspires you, this lecture series inspires you to take this problem and solve this. Either this or the transcendentality of the Euler-Mascheroni constant. So this was my talk. This was my time. Thanks for showing up. Thanks for your enthusiasm. Hope this helps. And this also will serve as a introduction to multivariable functions. So multivariable complex functions. So videos in the complex analysis playlist, I will jump to directly talk about the types of integrals we did in this video. With contours like this, with branch cuts like this, I'm directly going to jump there, because this video, for people who need it, I've made this video now. So see you. Please like and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Digamma, and see you in the next one. Thanks. This was really long.